Hello viewers, welcome to this video lecture program on electrophoresis. This is Ramakrishnan, Assistant Professor from Department of Biochemistry, St.Joseph's College, Cuddalore. In today's program, I am going to discuss the basic principles involved in electrophoresis, the factors which affect the mobility of the particle during electrophoretic separation, the next part of very first introduced electrophoretic system called tissue moving boundary electrophoresis. Under that, the basic principle involved instrumentation, merits and demerits of tissue moving boundary electrophoresis. There are so many methods available for separating a compound from the mixer in analytical biochemistry, but electrophoresis is the dominant one used for separating the macromolecules. The basic principle involved in this method is the particle for separation should be a charged one. For example, DNA, protein, etc. DNA totally having the negative charge because of the presence of phosphate ions. Similarly, proteins are all either positively charged or negatively charged based on the nature of the amino acid present in that one. If a protein is rich in basic amino acids such as lysine, arginine, and histidine, those amino acids are all rich in cationic one. And same way, if a protein is rich in acidic amino acids such as aspartic acid and glutamic acid, those proteins are all negatively charged one. Therefore, separation will be attained. Whereas the chargeless substances such as carbohydrates are not separated by this method. So in this method, the separating device should contain two electrodes. The one is having the negatively charged electrode is called a cathode, and the positively charged bearing electrode is called a anode. These two electrodes will always be immersed into an aqueous medium called a buffer medium. Based on the nature of the molecule separation, the buffer will be selected. The particle to be separated should be placed in between the two buffer reservoirs and attached with the help of a wick or gel based on the nature of the separation system. For example, if it is agarose gel electrophoresis means it will be attached with the help of a wick, or even it may be immersed into the buffer called a submarine gel electrophoresis. Similarly, in acrylamide or polyacrylamide gel electrophoresis, the separating medium will be a gel. It will be in contact with the two buffers directly. So the compound to be separated should be placed into the medium, and while applying the electric field or applying the current based on the potential difference and flow of current, the particles will be moved towards the respectively oppositely charged electrodes. For example, if the separating particle is cationic one, it will be migrating towards the cathode. And similarly, if the separating particle is a anionic one, the particle will migrate towards anode. Simply, cations move towards cathode and anions move towards anode during electrophoresis. During electrophoretic separation, the major factor which governs on separation of particle is determined by electric field. It is defined as the force per unit charge. From this image you will understand a molecule which is moving towards an oppositely charged electrode because of the applied electric field. During that movement, there will be a resistance generated by the medium, that is an opposing action, that is the frictional force and electrophoretic retardation force that will reduce the movement, and another one is the electrostatic force. So these two forces will govern the movement of the particle. The one which is leading will achieve the function. For example, electrostatic force is dominant one, means separation will be easier and faster, whereas the retardation force is high, means movement of the particles gets slow down. Rate of separation of a particle in an applied electric field is mainly determined by voltage. So that means the potential difference between the 2 points of electrodes is high, then the travel of the molecule will be very fast, or in other words, separation of the material will be very easy. On the other hand, if the voltage is low, separation will be less. That means voltage and separation is directly proportional. Second one is current. It is the rate of flow of electric charge. Current is generated due to the potential difference applied between the two electrodes such as cathode and anode. It is a continuous and uniform flow of electrons around the circuit that are being pushed by the voltage sources. The second dominant character which determines the rate of separation of a particle in an applied electric field is governed by the separating molecule. The major characters of the molecule which governs the separation of particle is charge, size and shape. The net charge of the molecule what we are going to separate is high, means the rate of separation is very fast. That is, net charge is directly proportional to the rate of separation. And the next one is size of the particle. If the size of the particle is very huge, rate of separation will be less, and size is small, means separation will be fast. This is inversely proportional. That means size of the particle is inversely proportional to the rate of separation. This is because of the frictional force generated by the huge molecules. And the third part of the sample is shape. Generally, spherical and ovoid molecules will migrate in a faster manner during electrophoresis than the aspherical and irregular shape, because aspherical and irregular shape molecules will generate more friction with the medium, therefore rate of separation will be less. This slide gives the simple equation for relating the different factors which governs rate of separation. V is equal to A into Q by F. V is the velocity of the migrating molecule, and E is the electric field in volts per centimeter, and Q is the net electric charge carried by the molecule, and F is the frictional force experienced by the molecule during separation. This equation relates the rate of separation. That means rate of separation of a particle is inversely proportional to the frictional force, directly proportional to the applied electric field, and net charge of the molecule. The third part which governs the rate of separation of the particle is called buffer medium, what we are using for separation. That is the two electrodes which is immersed into this aqueous medium called a buffer medium. Buffers are the substances which contains a weak acid and its conjugate bases. These are all the potential source for generator of ions and helps for the flow of electrons. These substances maintain a constant pH throughout the medium and favors for better separation. The most commonly used buffers are in electrophoresis are EDTA, formate, pyridine, tris buffer, barbiton, acetate buffers. Buffers should never bind to the molecules which is to be separated. That is, it is chemically inert. We have to select such kinds of molecule as a buffer. Similarly, the separating medium should also be chemically inert with the particle what we are going to separate. This slide shares the overall factors which governs during rate of separation in electrophoresis. The major factors are applied electric field, the sample characters, and third one is buffer nature. In applied electric field, voltage, current, and resistance are the factors which governs. Voltage is directly proportional to the rate of migration. That means high voltage favors for more separation. High current will also favors for more separation, and the resistance is inversely proportional. That means increase in resistance decreases the rate of migration. The second character sample, which is having high charge in the molecule, which is having better separation. Then size is inversely proportional to the rate of separation. And shape, the molecules which is spherical and ovoid will move in a faster rate than the aspherical and irregular shape. Then third part is buffer nature. If the buffer which is having good ionic strength and having very good pH maintenance characters will help for better separation. The very first electrophoretic technique was first introduced by Swedish biochemist Arne Tiselius in 1930, and he received Nobel Prize in 1948 for his invention. In order to honor the inventor, this electrophoretic setup was called as Arne Tiselius moving boundary electrophoresis. This electrophoretic system is very simple model in which a U-tube quartz crystalline material is taken, and the two edges of the U-tube was having the cathode and anode. The two electrodes are immersed into a buffer solution. Here there is no specific separating medium. The buffer itself acts as a separating medium. The compound to be separated should be placed in the center of the U tube. While applying the applied electric potential, the material present in the particle or the charged component will be migrated towards the oppositely charged electrode in a form of a cloud, a layer, so called moving boundary. That means a boundary will be observed during the separation, so called the Tiselius moving boundary electrophoresis. In this method, the movement of the compound will be keenly observed with the help of a external optical devices such as Schiller optical system or Rayleigh interferometric system. This picture depicts the 2D image of Tiselius moving boundary electrophoresis. The setup U-tube quartz crystals were filled with a buffer solution, and the two terminals of the U-tubes containing the two anodes and a electrode. The buffer solution middle part is having a opening system. That is, in the tube it is having a opening system. Through that, the sample for what we are going to separate should be injected. Here in this model, a compound which is having three substances such as A, B, and C were placed. Here, A is a anionic substance, B and C are cationic substances. So during the separation, anions move towards anode and cations move towards cathode. Therefore, we will see the opposite direction of movement. A that is towards the anode, B and C towards cathode. Even though in the B and C, pure B is moving in a faster rate than the C because it may be differ in the size or shape or total net charge. While looking the applications of Tiselius moving boundary electrophoresis system, separation of compound will be in a high biological activity because we are not using any separating medium, so the buffer itself acts as a medium and it will give the protein in the native form as such. And moreover, the separated protein will be a highly sensitive in nature. Even in 0.005 mg per ml will also be separated. The demerit of this system is protein or any compound separated is not in a distinct separating medium. Therefore, recovery is very difficult. And additional, it requires a separate monitoring system such as relay interferometric system or cellular and optic system.